Today, we're dealing with a new topic called linear inequalities. Does somebody have a question? Okay, so a linear inequality should sound partially familiar. The word linear, we know what that means. Linear equations are lines, right? So take a look at this first box on the left. This is a linear equation. Y equals x plus 3. Linear equations have equal signs in them. That's what equation means, is equal, right? So that makes sense. And we know how to draw a graph of an equation. You find your m, you find your b, you plot your b on the graph, and then you use your m, your slope, to figure out where your next point is, and you can draw a line. So we know how to draw lines. This line that we drew using y equals x plus 3 is basically a solution set. Every single one of these red dots that I'm drawing along here is a solution to this equation. So basically, if I pick any one of these points, let's say 0, 3, and I plug it into my equation, we will get something that is true. So if I plug in 0, 3 for my x and my y, I will get a true statement. That's what a solution set is. Each one of these red points, and any red point I put along this line, is an answer, is a true solution to this problem. So that's a linear equality, and we've dealt with those before. But today, we're going to talk about inequalities. Instead of having an equal sign, like y equals x plus 3, we're going to have something slightly different. We're going to have something like a less than, or a greater than, or a less than or equal to, or a greater than or equal to. Solution sets for this type of problem are not just a line. They're basically like half of the entire plane. The line y equals x plus 3 is what we call the boundary line. So notice that these two lines are actually the same. This one's just a boundary over here. But because it's not strictly equal, because it's technically less than or equal to that line, we don't need just the boundary line. We need everything below it as well. Less than or equal to it. Less than means below. So all of these points down here, everything below that line, is also a solution. I didn't have to draw it so dramatically, but there we go. All of the points in that blue region, in that shaded region, are solutions. So there's some notes here. The shaded half plane represents the solution set for the linear inequality. And let me prove it to you. If I pick any point over here in this region, how about 4, 1, and I plug it in to this equation, I will get a statement that is true. For instance, if I plug in 4 for x and 1 for y, I get the statement 1 is less than or equal to 7. That's definitely true. So all of these points over here would be solutions in the sense that when you plug them into this equation, it checks out. That's what we're dealing with here. All right, so let's move on to some examples. I'm about to throw a curveball at you. We have two examples here with a shaded graph. We're going to start with the one on the right, which is a little strange, I know, but we're going to do the second one first. So take a look at this picture. Any point in the shaded region or along the boundary line is a solution. So shaded points and points on the line are going to be solutions to this equation. So let's start with the first example. We're asked to find 0, 2. Let's draw that on the graph. Find 0, 2 on your coordinate plane. We're starting off with a tough one to see. So I could be wrong about this because I'm half blind, but I'm pretty sure that 0, 2 is like right on the line. You don't think so?
I think it's like right off.
It's like very, very, very close. Like the next one up would be it.
So you think 0, 3 is on the line?
Yeah.
Okay, I trust your eyes way better than I trust my eyes. So the consensus in the classroom right now is that 0, 2 is actually just outside of the line. It's just to the right of it. So it's in the non-shaded area, which would make this not a solution. If it's in the blank area, it's not in the shaded area, and it's not on the line, it's not a solution. Let's look at our next example. -2, 1. This is clearly right in the middle of the shaded region. This is definitely a solution. So we're going to get a yes here. The next one, 3, 2. This is clearly outside of the shaded region, so this is a definite no. And 0, -5. Looks to me like another big no. So only one of these points happen to be a solution, just based on the randomness. All right, so I said we're going to do the second example first. Now let's go back to the other example, the one we skipped. The reason why I wanted to do this one second was because there's something weird going on here. We haven't talked about this yet. Dotted lines represent points that are not solutions. With a solid line, the points on the line are solutions. But what a dotted line represents, or a dashed line represents, is that the points along this line are not solutions. So you have to pay attention to the boundary line itself. Is it solid? Is it dotted? And then you have to remember what that means. So let's tackle this example. Keep in mind the shaded region is still what the shaded region was before. So shaded regions are always solutions. It's just the boundary line that's a little different here because of the dotted pattern. So let's look first at 3, 1. That's pretty easy to find on our graph. Is 3, 1 a solution to this equation? Certainly. That's right in the middle of our boundary. I'm sorry, right in the middle of our shaded region. What about the next one? The next one's a little tricky. Let's find -2, -2. Okay, so unless my old eyes are tricking me again, which they very well might be, I think that's right on the boundary line. What do you guys think? Yeah?
Yeah, but it's because of the dotted line, it's a no.
I like that. So virtual students, why don't you type in the chat whether you think this -2, -2 is a solution or not. Just type yes or no. Yes for solution, no for not. We've got some mixed reviews. So the point is on the boundary line. It's right there on the boundary line. And boundary line points are not solutions if the line is dotted. We've got half the class saying yes, half the class saying no. This is very interesting to me. So this is a dotted line. So these points are not solutions. Any point along here, any point on this line is not a solution. So I'm really glad you guys are thinking through this and trying to guess and figure it out. But the answer here is no. Boundary point lines are not solutions if we have a dotted line. If you have a solid line, they are solutions. If you have a dotted line, they're not. So it's just another wrinkle that you're going to have to try to remember. 2 more to go. Let's try the point 0, -4. That looks to be about right here. I think that's far enough away to tell that that's definitely not a solution. That's outside of our region. And 5, -2 looks to be inside the region. All right, looks good. So that's what we do when we're dealing with a visual. This is how we can identify solutions using a picture of a graph. But in the next few examples, or next couple examples, we don't have a picture. We have a formula, an equation. We're looking at y is less than x minus 1. And we are trying to figure out whether this is a solution, this is a solution, or this is a solution, or this is a solution. We don't know. So the truth is, you can have tons and tons of solutions. We're just trying to figure out which ones of these are and which ones aren't. So another word for a solution, I alluded to this at the very beginning of class. Another word for a solution is something that makes your equation true. So if we look at each of these points, starting with -4, 3, this is an x value and this is a y value. If we take this x and take this y and plug it in to our equation, if it gives us a true statement, then it's a solution. We're looking for truth here. So let's take this point, -4, 3, and try that out. So for y, we're going to plug in 3. And for x, we're going to plug in -4. We'll want to simplify this just a little bit to make it easier to read. On the right-hand side, -4 minus 1 gives us -5. Is this a true statement? 3 is less than -5. No, not at all. -5 is way smaller than 3. So this is not true. So that means this is not a solution. Now let's work on the second point. So now we're going to repeat that process. We're going to take 2, 6. We're going to plug it in. We're going to see if it's true. So 6 goes in for y, and 2 goes in for x. Simplify the right-hand side, and we end up with 6 minus 1. I'm sorry, we end up with 6 is less than 1. Is that true?
No.
Heck no, it's not. Thank you, Miles. That is absolutely not true. So this is another no. This is not a solution. Next question, 0, 1. We're going to plug this in. 1 is less than 0 minus 1. Simplify that. We get another weird statement. Is this one true? Is 1 less than -1? Is 1 smaller than -1? No. Positive numbers aren't smaller than negative numbers. That's crazy. So I didn't write this problem. I personally don't even know where it came from, but whoever wrote this problem really liked putting false answers on here. Because we'll see even in our last one, when we plug 5 in for y and -1 in for x, we get 5 is less than -2. That's also not true. So this is just straight no's. No, 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 no. None of these are solutions to this equation. I do want to clarify, though, this has nothing to do with the problem. This isn't like, oh, I guess this problem just doesn't have any solutions. No, if we were to draw this on a picture, it would look something like this. So literally, any point over here would be a solution. Like, this would be a solution, this would be a solution, this would be a solution. It's just whoever wrote this problem didn't pick any of these points. They only picked points up here for some reason. I don't know why. So they all just happen to not be solutions. But there could be plenty of solutions to this problem. That's just a coincidence. Okay. Any questions so far? All right, let's move on to the next one. This next one is the same exact concept, but it involves a little bit more work because the arithmetic's going to get a bit stickier here. Let's look at our very first point. Is -1, -3 a solution? Well, let's plug it in and find out. 3 times -1 plus 5 times -3 is greater than -15? We don't know. Let's find out. If we simplify this a little bit, 3 times -1 gives us -3, and 5 times -3 gives us -15. And don't forget about your other -15 over there. When we simplify the left-hand side, we end up with a -18 is greater than -15. Is this true?
Oh, wait, no, it's not.
It took some people a minute. Yeah, don't be fooled by this. This is tricky. We see 18 and 15 and we're like, well, duh, 18's bigger than 15. But when we're talking about negatives, it's actually the opposite. Think about starting at 0 and you count all the way down to 15, but then you have to count down even further to get to -18. So you're going down 15 and then down 3 more. So -18 is actually smaller. It's lower. So this is false. This is a no. Whoever wrote these problems just loves the word no. Let's try the next one. Let's plug in -4, 2. And hopefully this is starting to feel boring. You know why? Because that means, okay, I get it already. This is easy. I understand. Let's move on. So if you're starting to feel bored, think of it as a good thing. All right, when we simplify this, we get -12 plus 10, which simplifies down to -2 is greater than -15. Hey, finally, something that's actually true. -2 is bigger than -15. We can put a check mark here, a smiley face, a thumbs up. I don't know how to draw a thumbs up. Good enough? Yay, we finally have a solution. Next example, let's plug in 5 and -1. I'm getting a little faster now because mostly this is just arithmetic. When we simplify the left-hand side, we should end up with a +10. Is +10 bigger than -15? You betcha. 1 left. 3 times 4 plus 5 times 0. Greater than -15. I love plugging 0 in because it just makes things disappear. Makes it nice to simplify. All right, so when we get rid of that 5 times 0, we end up with 12. 12 is greater than -15. Is that true? Yes, sir. Yes, ma'am. Yes, everyone. There we go. So on this example, we actually ended up with 3 points that were solutions. And there are many more out there. We were just asked to look at these. So this isn't too bad. It's a lot of scratch work. It can take up quite a bit of paper, but it doesn't take a lot of brain power. Let's talk about how we ourselves can create these graphs. So far we've talked about if we're given a graph or if we're given a formula, we can identify a solution. We can figure out what the solutions are. But now instead, we're going to actually draw our own graphs based on formulas. So flip your paper over. Yeah, we have a whole other side to do. We got this. Flip your paper over. We're going to do the back now. For this side of the paper, we're going to talk about how to go from basically a formula into a picture, into a graph, and how to draw it, how to shade it, everything. So the first thing we need to consider is the symbol that's in the equation. If our symbol has equal to components, so like less than or equal to, or greater than or equal to, we're going to use a solid boundary line. And remember, solid boundary lines represent points on the line are solutions. So you might want that on your guided notes. There's a good reminder, good place to have a reminder about that. When it comes to a dotted line, we've talked about this briefly. Dotted lines are used, or dashed lines are used, when the symbol does not have an equal component. So it's not a greater than or equal to. It's just strictly greater than, or it's strictly less than. These types of equations will get a boundary line that's dotted, and the points on the boundary line are not solutions. So you make sure you have that in your notes too. So let's just talk really quickly, this should only take us a minute, about whether these 4 examples would have a solid or a dotted line. We don't have to do any math. We're just going to say out loud whether they each have a solid line or a dotted line. And these pieces of information right here are all you need, the 2 things I circled. So first, is this going to be solid or dotted? Call it out. Solid. Good job, everybody. And students in virtual, feel free to type it in. For the next one, solid or dotted? You guys probably can't type as fast as the people in class can yell. We got a lot of dotted. All right, third example. Dotted again. And last example. You betcha. So it's really easy to do this when you have the information right above it, but down the road in the future, you have to remember this. So try to come up with a little way to remember when it's solid and when it's dotted. You know, come up with a mnemonic device or something like that to make sure you remember which is which. All right, so after we figured out whether our line's going to be solid or dotted, we actually have to draw the line. So you guys know how to do this. We've been doing it for weeks now. You get your equation in the form y equals mx plus b, which means y is by itself on the left. You get y by itself on the left. You find your m, you find your b, and then you draw your line. You just have to remember whether your line is solid or dotted when you draw it, but that's about it. Finally, once you draw your line, then it's time to shade. And to decide which side to shade, you look at whether you've got a greater than or a less than. If it's greater than, you shade up or above. That makes sense. Greater is higher, bigger, above. That makes sense. And less than is going to be the opposite. If it's less than, you shade below. Remember that you always have to have y on the left first, though. That's really important. You have to get it in this form first before any of this other stuff to apply. So let's jump into a quick example. If you look down just a little bit, we've got 4 examples here. We're going to start with example 1. Y is less than 4. Are we going to be using a dotted line or a solid line? Dotted. You betcha. So I'm going to actually write that over here just so I don't forget later. Trust me, it's really easy to forget. So I'm going to write dotted. Weird floating D. Then we need to get this in slope-intercept form. Y equals mx plus b. Well, where's my x? Right? So if this were like y equals 4, but we wanted it in y equals mx plus b, we would write it like this. 0x, right? Because there is no x. It disappeared. It's gone. So there's a 0 there. We don't normally write this. This part right here would just disappear. So we don't normally write that out. But when we're trying to put it into y equals mx plus b form, we want that 0 there because that shows us that our m is 0. Sorry, I should have written it as y equals 0x plus 4. So do you see how these two things are exactly the same? Y equals 4, y equals 0, x plus 4. All right, so we're going to use this to identify our M and our B. Let's draw our line. We start with B, which is positive 4. 1, 2, 3, 4. I think that's about here. My y-intercept is positive 4, so that's where I cross the y-axis. What's my slope? 0. So my rise over run is 0 over 1 or whatever, 0 over something. So that means my rise, I go up 0. So that's just flat. A slope of 0 is always just a horizontal, flat, straight line. That just goes straight across, slope of 0. All right, time to draw our line. Go ahead and do that on your paper. Draw your line straight across. Did everybody remember to make it dotted or dashed? So you don't want your line to connect all the way across. You kind of want it to look like dashes. So make sure there's some obvious space in between your lines here so it's clear. And I did my points really big, so mine looks kind of funny. I can even kind of redo this so it doesn't look so strange. So your line could look something like this. Just a dashed line going straight across at 4. Okay, so we figured out dotted or dashed. We drew our line. Now it's time to shade. This says y is less than 4. Are we going to shade above or below for a less than? Below. It's common sense, right? We don't even really have to think about it. So shade below. So just below that, going all the way down forever and ever and ever. Just stop when your hand gets tired. It doesn't have to be pretty. It's got to be obvious where you're trying to shade. And don't shade so much that I can't tell whether your line is dotted or dashed. So notice, like, I left some space so you can still see my line there. It just makes it hard for me to read. I'll be able to tell which side you're shading, even if you just, do a little tiny shade there. Okay. So 1 was a little bit weird because it wasn't an mx plus b form from the start. But number 2 should actually maybe be a little bit easier than number 1 was, because this is in mx plus b form. Just looking at number 2 from the very beginning, I can very quickly say, oh, okay, well, this is my m and this is my b. We can go ahead and start drawing our line. So our y-intercept is -3. That's right here. And my rise over run is -1 over 2. That's down 1, right 2. Down 1, right 2. Down 1, right 2. We can even take our pattern up in the other direction since I'm kind of running out of space there. What? Floating point. All right, so time to draw our line. Do we want a dotted line or a solid line? Bingo. Draw that dotted line. And are we going to shade above or below? Below, because we've got a less than symbol. So yeah, absolutely, we're going to shade below it. So this area right over here. Going down and down forever, but I don't have the patience to draw that long. All right, guys, I think we have time for example 3. So example 3 is the same type of problem, but there's something we have to do at the beginning. We're supposed to have y by itself on the left. We don't have that. We have y by itself on the right. So we need to rearrange this. So what I'm going to do is I'm going to take this formula and I'm going to flip it around so that the y is on the left. When I do that, though, I have to be very careful because it switches the sign. Go ahead. Is that all you needed? It switches my sign around. So I'm gonna make a little note here so that this isn't confusing. Think about this real quick. Let's say I had 5 is greater than 1. That's kind of obvious, right? But if I switch them, if I flip them around, then the sign has to flip too. Because now the bigger one is on the other side. So whenever you take your two sides and you just flip them like that, it's going to change the sign's direction. So it was a less than or equal to, but it becomes a greater than or equal to. So we've just flipped the whole thing around. That's our first step, to try to get y by itself on the left. Then we want to make sure that this is written in mx plus b form. We have an m, x, but where's our b? Well, we kind of need to fill that in ourselves. So I'll put a +0 here on the end. Helps me kind of see that that's our b. Time to draw. Start with your y-intercept, which is 0. Your slope then helps you find your next point. So our slope is always a fraction. Our slope is 3/1. So our rise is 3 and our run is 1. So 3/1. We'll go up 3, right 1. And ran out of space, so I went down in the other direction. Dotted line or solid line? Solid. Very good. Very good. So that's going to just look like a normal, regular, everyday line. There we go. And shading. When we look at the shading, we're not going to look at the original symbol. We flipped that around. We switched it. We changed it. You need to look at the symbol as it is at the end, when y is on the left. So we're looking at the final symbol with y on the left is a greater than or equal to symbol.
It's greater than, so it's above.
Perfect. Nicely said. It's greater than, so it's above. And you're McKenna?
Yeah.
Appreciate it. So McKenna told us to shade above. She nailed it. We're just going to shade right above that line. Yeah, I'm so sorry. I need to approve your hall pass. Okay, so I'm not used to like hall passes and things like that. I taught college before this. Students would just, come in and out. So if you ask me to use the restroom and I tell you to make a hall pass, I am immediately going to forget that I told you that. So you have to remind me, like, hey, can you approve my hall pass now? Did you have to set it up under Mrs. Montgomery's name still?
I put it under mine.
I don't think I have one on here, do I?
It popped up.
Huh. Okay, I will try that for tomorrow, but for right now, can you just do it under Mrs. Montgomery?
Yeah.
Well, that's convenient. All right, so I know we've got like 8 minutes left of class, but number 4 is so different from numbers 1, 2, and 3 that I kind of don't want to do this one today. I want to save it for tomorrow because it fits better with tomorrow's material.